cool. All right, so this is out of 10.2, and this is problem 1, which says that I want to rewrite this system of differential equations in matrix form and verify that a given function satisfies the system for any choice of constants, right? So first things first, I should rewrite this as a matrix function. Have you guys all had some kind of matrix theory?
Yeah.
Besides the video, not
I
really.
think a lot of people have, but I think there's a couple who haven't.
Not universal. Okay, so let's see. You all have at least had vectors, I think. So this kind of left-hand side, I'm just writing as a vector y1 and y2, and putting a little prime on that thing. If you want to think about that as a Calc 3 vector, that would be kind of the vector y1 comma y2. And it seems kind of clear that I'm differentiating that, right?
Yeah.
Okay. Then on the other side here, I pretty clearly have some kind of combination of y1s and y2s. And so if I remember back to how to express a set of equations as a matrix, I maybe think to myself, okay, so that's 2 and 4, that's this 2 and that 4, and then 4 and 2, and that's this 4 and that 2. And then this is times the vector y1, y2. Does that make sense? I'm trying to find if I have anybody that hasn't seen this level of matrix used before. Does everybody know?
Good. Understand.
I understand.
Does anyone not understand? Okay. Hearing none, I'm going to assume that you were with this. So then as a vector equation, this is y prime is this matrix 2, 4, 4, 2 times the vector y. Okay, so if I want to check this, I really have this proposed solution here, right? And this thing doesn't really feel like a vector right now, because frankly, it feels like two vectors and some stuff going on. So anybody want to tell me what some of that stuff going on is?
You keep cutting out. I don't actually know what you asked.
Well, damn it. Let me try a slightly different microphone here. Okay, so before, when I was cutting out all over the place, I was asking this proposed y that they've given me, right? Y equals c1 and times the vector 1, 1 times e to the 6t plus blah, blah, blah. That doesn't seem like one vector. And yet they're claiming that that's kind of a vector solution, right? So what is this other, like, how is that a vector? Oh, so you're, whoa, what the hell was that? So you're saying that I can maybe say something like, okay, so y is, and maybe that first thing becomes what? What does that first vector become? Yep. And then a negative on the bottom. Oh, negative that same stuff. Okay, and what is the operation you're doing there? that's it's multiplication by specifically a close. It's a vector in this case, but yeah, we could call that a matrix, but it's also specifically what kind of thing that we're multiplying. You said it was a number. No, it's not, but it's a scalar. It is. It's a. It is scale. It's a scalar function, right? But the operation you're using is the scalar multiplication operation. And then this sum here represents what? What is that plus sign in the middle here? Good. Addition of. Good. That's vector addition, right? Mm-hmm. Perfect. Perfect. Okay, then the question is, so now that I have that written down in this new way, can you calculate y prime? Yeah, okay, so you just take the derivative of it. So you got 6c1 e to the 6t. Oops, that's going to be minus 2c2 e to the minus 2t. And 6c1 e to the 6t plus 2c2 e to the minus 2t. Okay, so this thing here is the left-hand side of my equation, right? And if I'm verifying, so they told me to verify the given vector function satisfies the system. So that really means check that the left-hand side equals the right-hand side. Right? Okay, so I have the left-hand side calculated. So now what's my next step? If I totally vanished. So I think what I was saying before I stopped was, if I have just calculated the left-hand side and I'm supposed to verify the left-hand side and right-hand side match, what am I now supposed to do? So I have the left-hand side. I'm supposed to yeah, I really need to calculate the right-hand side, right? Okay, so if the right-hand side is supposed to be this matrix 2, 4, 4, 2 times the vector y, then I guess I better go do that, right? So that's going to be, I need to multiply the matrix 2, 4, 4, 2 by the vector. And in this case, it's a bit obnoxious because it's c1 e to the 6t plus c2 e to the minus 2t. Can whoever's scraping please stop? c1 e to the 6t minus c2 e to the minus 2t. Right, so I just need to execute this matrix multiplication. Right? And so failing my usual method to do this is that I talk about picking up the vector and twisting it sideways and then dropping it on. But it's not exactly possible for me to make that gesture with this setup. So I'm going to think that this is going to be the first row dot product with y and the second row dot product with y. Meaning the row is going to be, this is row 1 and this is row 2. So row 1 is the vector 2, 4, and row 2 is the vector 4, 2. And then I'm going to dot product with this y vector. Does that make sense? Have all of you that have had matrix or linear algebra had this row multiplication picture beaten into your heads yet? Good. Yeah, except that in this case, right, the calculator's probably not going to be very good at this because it's all full of functions and whatnot. All right, so I think I'm going to get a vector, right? That's going to be my answer here. And it's going to be 2 times the top component of y. So that's going to be c1 e to the 6t plus c2 e to the minus 2t plus 4 times the bottom component. So that's going to be c1 e to the 6t minus c2 e to the minus 2t. And then the row 2 dotted with y is going to be 4 times the top component. So c1 e to the 6t plus c2 e to the minus 2t plus 2 times the bottom component, which is c1 e to the 6t minus c2 e to the minus 2t. You guys all with me on that? Okay. Good. So I'm going to get 2c1 e to the 6t plus 2c2 e to the minus 2t plus 4c1 e to the 6t minus 4c2 e to the minus 2t and 4c1 e to the 6t plus 4c2 e to the minus 2t plus 2c1 e to the 6t minus 2c2 e to the minus 2t. Okay, then what? Perfect. Kick ass. Okay, so this thing here is the right-hand side. And Glenn, you were... Did you... No, all Emma did was combine like terms. So she's looking at the... Okay, so I now have a right-hand side and a left-hand side that I'm supposed to check if they're the same. Are they? Are these two things the same? Yes. Okay. One of them is y prime. the other one is the matrix 2, 4, 4, 2 times y. Because they're the same, that means that y is in fact a solution of this system of differential equations. And so what I can do is I can say, check. Y solves this system. Period. Cool. Questions? So why does it feel like I'm starting differential equations all over again? Why does it feel like I'm starting differential equations all over again? Why does it feel like I'm starting differential equations all... Fucking hell! All over again. How about because I am? Right? I know how to solve single differential equations now. And so now I'm going to start over again with systems. The good news is it goes a lot faster because I already know how to do some things. Does that make sense? Okay, so right now this feels like magic, probably, right? So, let me maybe say some one thing here. So the like, where did this thing come from question, like how did they do this, is really kind of interesting. I just put a rectangle over the top of it. Matt already dropped it into the Discord. So when I look at this differential equation here, because this is... So when I look at this thing, I'm seeing something along the lines of like y prime is ay, right? Where a is a number-ish. And that makes me feel like I should be able to say something like, well, probably y is e to the at, maybe with a constant, I guess. Right, it's like some constant times e to the at. And the thing is, that's sort of where this is coming from. So the reason that we got these kind of special values here, there's these like two vectors that seem very special, this 1, 1 and this 1, minus 1. So if you take your matrix here, your 2, 4, 4, 2, and you just think about what happens when you multiply that by the vector 1, 1, you get out 2 plus 4 and 4 plus 2. And that's 6 and 6, right? Which is 6 times what you started with. And you guys see that? Does anybody recognize this thing from linear algebra class? Okay. Okay. What if I rewrote that as 2442 minus 6600 times 1 equals 0? Yeah, there's kind of an invertibility criteria here. That's not quite what I was looking for. Let's see. So that would be. It also looks like this. Which is yeah, so what you might notice here, right, is that if you have a matrix and an eigenvector, that along that vector, the matrix acts like multiplication by a constant. And so if you can find the eigenvectors, then you can solve differential equations like this by saying, okay, so I have this matrix 2, 4, 4, 2. If I find the eigenpairs for it, the eigenpairs are the value 6, the vector 1, 1, and the value minus 2, and the vector 1, minus 1. And then I can just put them into this form where I do y is c1 times the first eigenvector e to the eigenvalue t plus the same for the second eigenpair. We're going to do some more of that later, but for right now, I just don't want it to be a mystery that this doesn't appear from nowhere. There's a relatively straightforward way to get a hold of it. Does that make sense? I'm not going to ask you to compute eigenpairs yet. We'll get there in a couple of days, but I just want you to know that these solutions that the book is coming up with aren't arising out of nothing. Okay. Any other questions on this thing? Okay. So the process that I'm trying to illustrate here is the process by which you can both convert a system into a matrix equation and the process by which you can verify that something is a solution. Good with those? Okay, so where did I cut out in there, Frankie? Okay, so how about the two things I was trying to illustrate here are how to convert a system into a matrix equation, and how to verify that a solution solves a matrix equation.